Welcome to section 3 of the Bayes AI course. We're going to start data analytics, and we're going to talk about statistical estimation and A/B testing. First of all, most data scientists use R, an open source package with a lot of people having written programs for R. So I suggest you download R and RStudio and use this to do your data analytics. Here are the links to download R. As I said, RStudio is a nice interface to put on top of R. And there's a lot of packages and libraries available that people provide for R. Here's sort of the standard R commands that we'll be using. One of the big ones to remember will be LM, which will stand for linear model. Okay. Similar in some sense to Excel, but we'll just be focused on R. Okay, so let me start with a very, very simple probability model. So let's try and see if we can understand the stock returns of Google stock. So first of all, I have to define a random variable x. That'll be daily returns of Google stock, and I'll start with a very simple model, too simple of a model. I'll assume that the returns or log returns of Google stock are normally distributed around some mean mu and some variance sigma squared. And we can think of sigma, the standard deviation, as the volatility of Google stock. Now, I say too simplistic because when we empirically look at stock returns, we see that there's much more likely to have extreme observations. So this assumption of a normal distribution is too simplistic, but it'll at least give us some kind of idea of what to expect. Now, first of all, we don't get to see what the expected return mu is or the volatility sigma is. So we'll historically look at the returns of Google stock, and we'll use a random sample. So a very statistical concept is if you don't know your underlying Greek parameters, mu's and sigma squareds, we'll estimate them from empirical data. And of course, we've talked about it before, but the sample average x bar will be our estimator of mu. Sometimes we'll write mu with a hat to say that we've estimated it. And s squared, the sample variance, will be our estimator of sigma squared. And the n minus 1, because I've lost 1 degree of freedom by estimating the mean mu. So a simple model. Graphically, what does it look like? Here's the stock price of Google stock from 2005 to the end of 2019. And if we plot it on further, Google stock is now at 2,200 at the beginning of 2021. Now, instead of looking at the price itself, we'll look at the percentage changes or the returns on a daily basis. And we'll plot a histogram. And it's this histogram that we're modeling. And as we assumed before, we're assuming that this follows a bell-shaped normal curve. Now, there's a couple of things you can observe. Rather interestingly, Google stock stays the same. So here's the zero return level. Google stock stays stationary more often than you would have thought from a normal. And then it also has more extreme moves than you would have thought from a normal. So there's a number of places where this normal distribution doesn't fit. In the extreme tails, I think there's an observation here where in one day it lost 15% of its value, one day it lost 10%. And that's partly because there's other extraneous factors. For example, stock market crashes or earnings reports and other such things. Okay, but looking at our return distribution, the normal approximation is not too bad. with the caveat of these three places where it doesn't quite fit. Okay, so assume you invest all of your money in Google. Your job is to try and tell me what's your expected return on a 1 year window, how risky will that investment be, and what's the probability that I lose at least 3% in a day, to give you some kind of idea of what the movements do. So I simply load my Google return data into R, and I simply just use R to calculate my empirical mean and empirical variance, or standard deviation. And we see that on a daily basis, your best estimate of the expected return of Google stock is very, very small, 0.0007% per day, incredibly small, whereas your best estimate of the volatility is about 1.86% per day. And remember your statistical rule, 95% of the time the random variable will lie between x bar plus or minus 1.96 standard deviations either side, and what essentially a 2 standard deviation band would be about 3.7%. So you shouldn't be surprised if Google moved up 3.7% a day or down 3.7% a day. In return for taking that risk, you've earned a little bit of expected return every day. Now, even though that number looks extremely small, there's 252 trading days in a year, and if I multiply it up, what's happened to Google since it IPO'd is, on average, it's made 17.8% a year. And so you can see how this risk-return trade-off works. Now, let's answer that last question. Remember, we've done expected return, 17.8%. We've done the amount of risk, 1.86. On a yearly basis, we'd have to multiply by square root of 252, which is about 16. So approximately about 30% volatility on an annual basis. So single stocks are much more volatile than indices or portfolios of stocks. Okay, so how about losing money? What's the probability that I would lose 3%? So there's my minus 3%. So I take my normal model and I standardize it, take off my best estimate of the mean, divide by the standard deviation, and I see that a 3% negative return in Google stock on a standard deviation scale is 1.65 standard deviations. And again, if I go to R, what's the probability from a standard normal that I'm less than or equal to 1.65? It's about 4.9%. So essentially, one day in 20, or approximately once a month, I shouldn't be surprised to see myself lose 3% a day, and vice versa on the other side of the coin. I shouldn't be surprised to make 3% in a day. So a simple model which doesn't 100% empirically fix the data, but it gives you a good sense of what would happen if you invested your money into Google stock, in terms of the expected return I expect to make, in terms of the volatility risk I'm taking, and in terms of what's known as value at risk. What's the odds of a 3% drawdown? Okay, let me do another example out of the AIQ book. So Isaac Newton was famous for a number of things. The apple falling on his head, gravity, calculus. One thing that maybe people don't realize about him was that he was master of the mint. So he managed the English money supply in the 1720s. He was around when the South Sea bubble happened. He lost, I think, £10,000 back in 1720 when the South Sea bubble happened. So he invested money, lost money. He was also one of the proponents of the gold standard. So I think England was on a silver standard. Newton came in and switched everybody to a gold standard. And back then, English coins were made out of gold. And there was a large variability in the weight of these coins, because people would clip these coins. They would shave off a little bit of gold. And so Newton held something called the trial of the pix, which was designed to figure out whether the coins are good or not, whether the coins have been clipped or not. And so the idea was to weigh a whole batch of coins. It was costly to do one coin at a time. So he would weigh a batch of coins, 2,500 for example, and they were supposed to weigh 100 grams. And the idea there was for him to work out, and remember this is 1720, was him to work out what was the allowable margin of error for a sample size of 2,500. And so an allowable for one coin was 1 gram, and Newton just implemented that for the whole batch of 2,500. Well, of course, setting the bounds for an average of 2,500 being the same as an average of one coin is, of course, a bad mistake. So Newton, of course, this was before Gauss had come up with the Gaussian distribution, so before anybody knew anything about these probability distributions. What Newton should have realized is that the variability of an average, so remember that x bar is an average of the average weight of n coins, is the variability of a single measurement, that's our sigma, divided by the square root of the sample size. Just quickly, why square root? Well, if I looked at the variance of an average, variance squares numbers, so the variance would be sigma squared over n squared, and if I take the it would be sigma squared over n, and if I take the square root of that, I'd get my standard deviation, or the variability of the average would be sigma upon root n. And so what Newton should have done is, rather than go plus or minus 1, he should have gone plus or minus 1 upon the square root of 2,500, and that's a small number, 0.02. So he should have looked at a batch of 2,500 coins, measured the overall average. If the overall average was anywhere under 99.98, he should have realized that some of the coins in that batch were bad. Okay, so there's a good example, again, of using random samples, trying to understand the variability that you would expect in a random sample, and then being able to figure out whether something is wrong or not. Let me just put that into one slide. So the sampling distribution of x bar, remember that x bar is an average 1 upon n. The sum I goes from 1 to n of xi, each individual observation, where each individual observation is assumed to have a normal distribution with mean mu, variance sigma squared. So, excuse me. So my underlying assumption is I've got normally looking data. Then what's the distribution of x bar? Well, the mean stays the same. It's similar to our portfolio problem that we had in week 2. And the variance, as I said, becomes s squared upon n. And so the standard deviation of x bar, I'm using this notation here, s sub x bar will be s divided by the square root of n, sampling distribution of the sampling mean. And from that, we can compute something called a confidence interval. So in summary, our best guess at mu, if I wanted to guess the overall average, is just simply the empirical average x bar. How large of a mistake can I make? Well, that's governed by the s upon root n. And as a general rule, I will look at a 95% range of plausible values for mu. And so if I go 1.96 standard deviations either side, and it's the standard deviation of x bar I need to do, I'll get my 95% confidence interval. Now, what happens if I want 90% or 99? Essentially, what happens is this: the z-score level changes. I'll either use 1.645 or I'll use 2.58. So if I want to change the level of confidence, the more confident I want to be, of course, the wider the interval has to be. And again, you can see a number of other interesting facts that if my sample size gets bigger and bigger and bigger, my confidence interval will get tighter and tighter and tighter. Okay, so the idea of a confidence interval. Now, a related concept, which is very important in modern day world, a lot more models are used to make predictions. So if I want to decide what's the range of possible values for a single future observation, not just the range of plausible values for the overall mean mu, if I think about it right, I get an extra error variance that comes in for the single observation. So instead of x bar plus or minus, I'm using z sub alpha upon 2 to denote how many standard deviations, the so-called z-score, how many standard deviations I go either side of the mean. I'm going to get an extra, because there's an extra error term that comes in for one single observation. So a similar looking formula, but with this extra level of 1. And again, one of the other big differences is as n gets bigger and bigger and bigger, this last term will disappear. But of course, that first term, the inherent variability in one observation won't disappear. So my confidence interval my prediction interval can never be tighter than x bar plus or minus however many standard deviations you want to go times s. And again, it makes sort of sense that prediction intervals will always be wider than confidence intervals. And what are typical applications? Suppose I wanted to calculate sales in a particular Walmart store. Well, then it's really a prediction interval I want. If I wanted sales countrywide on average of all Walmart stores, then really I just want the confidence interval, and I wouldn't need to bother with the 1. So prediction intervals are always wider than confidence intervals, and as the sample size goes to infinity, the confidence interval will converge to a point, whereas the prediction interval won't. Okay, so we've done confidence intervals and prediction intervals for mean, mu, where we use the sample mean x bar. What about for a proportion p? So lots of problems when I want to work out confidence intervals for proportions. Well, again, same idea. I essentially use the empirical number of successes, p hat. Remember, x is counting up. It's counting up the numbers of zeros and ones. So x is counting up the number of successes. So again, I'm just using the empirical frequency of success to estimate p. And because I have a binomial distribution, remember the formula for the variance of a binomial is np1 minus p. I'm looking at the variance now of x over n, so I have to divide that by n squared. So I get my variance as np1 minus p over n squared, and n cancels, so I get p1 minus p upon n. Take the square root, and there we go. There's the formula for the standard deviation of a population. And I typically don't know p, so if I've had to estimate p, I plug in p hat. And again, the form for a confidence interval, and we could do the same thing with a prediction interval, we'll be looking at my best guess. So p hat is my best guess at p, what that underlying proportion is. I go however many standard deviations I want either side. So here again, I want my 95% confidence interval. And then I have to look at the standard deviation of p hat, which from above is just p hat 1 minus p hat divided by n. Okay. Quick example. Suppose Google is changing something in its search algorithm, and it wants to check how often do people click through. It wants to test algorithm 1 versus algorithm 2. Usually these things are very fine. The differences are very small. So suppose I take a sample of 2,500 for algorithm 1, 1,755 successes, 745 failures, as opposed to algorithm 2. And maybe algorithm 1 is the status quo, and I'm thinking, should I switch to algorithm 2? So I just immediately do my p hat. So I just go 1755 over 2,500 gives me my p hat for algorithm 1. I do my p hat for algorithm 2. Now, of course, the statistical question is, is the algorithm better, and is that for sure? Remember that there can just be random fluctuation. So is algorithm 2 really better than it looks like it, but is it really better? The difference is what? 0.025. And of course, to answer that question, you have to take into account essentially the Newton formula for the variability of a successive proportions. You have to take into account the sample size 2,500. And there's a couple of ways to do it. So let's start with way number one. Let's just take them separately, algorithm 1, algorithm 2, and let me just calculate my two 95% confidence intervals. And the issue is, do these intervals overlap? So the top interval goes from 0.693 to 0.711. The next one goes from 0.718 to 0.735. So it's incredibly close, and they don't overlap. So it looks to me as if algorithm 2 at the 95% level is better than algorithm 2. But maybe it's slightly more accurate to do the difference. So let's look at the standard error for a difference, because this is going to be the beginning of A/B testing for us. If I do the standard deviation of two averages, it'll look something like this. Remember, variance under independence will sum. So if I've got the variance of x1 bar plus the variance of x2 bar, then I take the square root, I get the standard deviation of the difference. And for our Google search algorithm, when we're going to look at the standard deviation of a difference in estimated proportions, I get a term that looks like this. Okay, so slightly more accurate to do the difference. Let's see what happens. If I was doing two means, it would be a formula that looks like this. If I'm doing two proportions, it's a formula that looks like that. And let's just plug in the numbers. So looking at the difference, I get a slightly better estimate of the variance of the standard deviation. So remember that algorithm 1 had a p-hat of 0.702. Algorithm 2 had a p-hat of 0.727. P-hat 1 minus p-hat over n, I get an overall standard deviation of 0.012. Now, if I do my confidence interval, remember this is for the difference, and it's at the 95% level. I've made it so I just can't decide that algorithm 2 is better than algorithm 1. It's right on that boundary of 0. If both numbers were negative, then algorithm 2 would be better than algorithm 1 at 95% confidence interval. But again, incredibly close. And again, remember that in a lot of these problems, there's what's known as a null hypothesis, an operating assumption, which I'm going to call H0, and then you're trying to see whether H1 is better than H0, or in A/B testing, whether A is better than B. Okay, another quick example that you can go over in the notes. Remember our Patriots example. They won 19 out of 25 tosses, and what's the data telling us about the probability of heads of these coin tosses? So again, p-hat, you would think it should be 50%. It's way higher. It's 76%. The sample size is very small. Again, sample size is very important in these calculations. The larger the sample size, the more accurate you get, and so the tighter the confidence intervals will be. But if I do my 95% confidence interval and I go through the math, I get a range that goes from 0.592 to 0.927. Why so wide? Well, we've answered that. It's because n is small. And what do we conclude? Looks different from 0.5. Of course, we would have to have more data to conclusively decide, but based on the sample size of 25, a small sample size, at the 95% level, the interval does not contain 0.5. So statistically, significantly different from 0.5 in our Patriots example. Okay, so here's just to conclude this little section of the notes. There's a number of things. A lot of statistical theory is to take random samples of variables, of random variables, and then to calculate estimates like x bar or p hat, or maybe a difference in x bars, x1 bar minus x2 bar, or p1 hat minus p2 bar. These things are random themselves. Need to work out the variability of x bar, the variability of p hat. That leads us to the standard error of each of these variables, and from that we can construct 95% confidence intervals. And then again, we could calculate 95% prediction intervals by adding an extra standard deviation in. And so we get a useful tool. We get to see a plausible range for the quantity that we're trying to estimate, and we get to start to be able to compare things. Is Google algorithm 2 better than algorithm 1? Does it look as if the Patriots have a coin where it's bigger than 0.5? Okay, so that sets me up nicely for what's known as A/B testing. And again, this is essentially the classical approach to what's known as hypothesis testing. So Neyman Pearson hypothesis testing. So I have one or two alternatives, H0 or H1, or A or B, and I want to try and figure out is A better than B or not. And I'm going to have to talk about something called a significance level alpha. I'm going to have to talk about something called a p-value. And again, we'll do it for our three different cases: means, proportions, and we'll come up with a test for smaller samples. This will be based on a t-test. Actually, for most of your life, you could just go through and do a t-test for everything. T-test will also work for larger sample sizes too. Okay, just a little aside. There's a very different solution if you're Bayesian to these hypothesis testing questions. And given that you've done week 1 and week 2, it would be remiss of me not to point you in a direction of where to look to do the Bayesian version of hypothesis testing. So there's a very famous paper by Edwards, Limon, and Savage in the 1960s. I think it's something like On Bayesian Methods for Psychological Research. And of course, the Bayes approach to hypothesis testing is very simple. I want to work out what's the probability of H0 given my data. So let D be data, right? And that's actually very different from something like a p-value. A p-value would be something like, what's the probability that t is bigger than t, given that H0 is true? And remember, we talked in the Bayes section, you have to be very careful about which way round. So if I have a two-sided test, it would be absolute value of t. You have to be very careful of which way round you have the conditioning. Probability of t bigger than t given H0 under the assumption H0 is true can be totally, and generally is totally different from the probability that the hypothesis is true given the data. And of course, if you're Bayesian, it's this one here that you want to calculate. And as I said, the classic papers, Edward, Limon, and Savage, pointing out all the big differences. And another interesting example where p-values give very different answers to the Bayes approach is something called Lindy's paradox. And again, the intuition of Bayes is sort of sensible. If I have in Lindy's paradox, as n goes to infinity, the probability that the null is true can go to 1 if the t ratio is held constant at, say, 2. And the intuition there is that if I have a very large data set, suppose I have 100,000 observations, and I get a t ratio of 2, the classical approach will reject H0 and say, okay, the p-value is less than or equal to 0.05. But if you think about it from a more pragmatic Bayesian perspective, with an incredibly large sample size of 100,000 too, if you've only got a t ratio of 2, you might sort of think that the probability of the null being true and that's what turns out to be true. Or another way of saying it is that the Bayes approach has like a natural mechanism for adjusting for the sample size. Sometimes it's called an automatic Occam's razor if you look at the literature. So A/B testing from a classical perspective has got a long history, and I think as time goes by, already people like the FDA and people that need to assess these probabilities at a very high level have realized that the Bayes approach is much more sensible than the classical one. Okay, so there's a little aside and something for you to look at further. So just a couple of quick, very simple examples, just so we get the idea. Maybe the most famous hypothesis test in history is the Coke Pepsi test. There's a lot of discussion of how you set up. We'll talk a little bit in a minute about observational and experimental studies. A lot of discussion about how you set up to test these things, double-blind experiment, neither experimenter or subject knows the allocation. Pepsi claimed that more than half of the Diet Coke drinkers said they preferred to drink Diet Pepsi. So let's just do a simple little example. So I've taken n to be small, and so the second that you look at that, you should realize that the standard deviations will be large, confidence bands will be large, and it'll be hard to figure out whether things are true or not. And in that random sample, basically p hat is 56, so p hat is 0.56. So it looks as if Pepsi's claim is true because 0.56 is bigger than 0.5, and a notation for this would be p0. What's our assumed probability under the null hypothesis? But of course, even though 0.56 is bigger than 0.5, the fact that our statistical evidence, we only have a small sample size, should already alert you to the fact it's going to be difficult to see if that's true at a high level of confidence. So how do you set up A/B testing? There's going to be a statistic. There's going to be a null and alternative. Typically, you're testing to see a mean equal to 0, or you're testing to see a proportion equal to a half, for example. And then there's going to be a sampling distribution of a statistic, a normal or a t. And again, it's basically calculating how many standard deviations is reality, is the observed that you see away from your assumed. So typically we'll replace mu by mu0, x by the sample observation, sigma by an estimate of its standard deviation, and we'll calculate a z or a t-score. When sigma's been estimated by s, we'll call it a t-score. This is sort of a famous calculation. Somebody called William Gossett, who wrote a paper under the name Student, was testing the quality of Guinness beer. And of course, the sample sizes for drinking Guinness beer are not that large, maybe between, say, 4 and 8. And he would look at the distribution of averages from testing batches of Guinness beer, and he would find that there'd be these surprising outliers. And this is the distribution of the average x bar. And of course, you would have thought it would have been a normal distribution, but you get these observations again in the tail of the distribution. And he realized that for small sample sizes, the distribution of this random variable, essentially x bar is normal, but s is something called the square root of a chi-square distribution. He realized that the distribution was something called a t-distribution, his student's t-distribution. And he came up with a formula for the probability density of a t, and it would basically account for the heavier tails. And just operationally, what happens is that when you calculate confidence intervals, instead of going 1.96 standard deviations either side, you have to go a little bit further, and you have to, given the appropriate degrees of freedom, you get a slightly wider interval if I have smaller sample sizes. And one nice thing about the theory is that as n goes off to infinity, the t-distribution ends up as a standard normal. So if n's bigger than about 30, you won't see any difference. Okay, so a very fun old story. The t-distribution was invented because somebody was testing the quality of Guinness beer in Dublin. Okay, so again, what's hypothesis testing? We've already talked about it. Set up a null alternative, set up a significance level, typically 5%, depending on the seriousness of the problem, sometimes 1%, sometimes even less than 1%. Google wouldn't want to change its search algorithm if there was any risk of something happening to it, so maybe even lower for a Google problem. So set up ahead of time. Step 3, a Z or a T statistic, and then a formal decision rule. So, for example, if I'm more than 1.96 standard deviations away, at the 5% level, so if my alpha is 5%, I would prefer H1 over H0. Or I would say I will reject H0 at the 5% level in favor of H1. Now we get to see an actual observed z-score. So what's the p-value? We need to work out what's the... So there's a couple of cases, either a two-sided t-ratio or a one-sided t-ratio, depending on your null hypothesis. And essentially, given the observed, I want to work out what would the probability be of something more extreme. And again, let me just remind ourselves, the p-value has no place in the Bayes approach to hypothesis testing. It does not directly compute the probability of H0 given D or the probability of H1 given D. So the p-value is just a pure artifact of classical statistics. And so the Bayes counterpart would calculate something quite different. And as a general rule, the Bayesian is less keen to reject the null hypothesis. And as I said, the Edwards, Lim, and Savage paper is really a classic with a lot of great examples in it to go look at. Here's a little plot. So a two-sided test, if x not equal to mu, if x bigger than mu, or if x less than mu. Those are the rejection areas that you would look at. So a quick little revisit of the Google algorithm. Again, I can do instead of the confidence interval, I can do a hypothesis test or an A/B test for the difference of probabilities. And again, the calculation in R is proportion test. Okay, there's my Coke Pepsi example again. Let me do confidence intervals for Coke Pepsi. Set it up as a hypothesis test. There's my p hat. There's my standard deviation of p hat. And if I go at the 95% level, or an alpha of 5%, I get. We've talked about it before. I get a very wide interval because my sample size is small. Excuse me. And of course, the underlying null is that no difference between Coke and Pepsi is at 0.5, and that lies inside the interval. So even though the observed 0.56 is bigger than the 0.5, at the moment the statistical evidence, that could have happened by random chance under null hypothesis H0. So no evidence at the moment to say that Pepsi's claim is true. How would we figure that out? Well, clearly the ultimate, the gold standard test would be just larger and larger sample size. As the sample size gets bigger and bigger, my 95% confidence interval will hone in on the truth. Okay, I could do it as a testing problem. I could do it instead of a confidence interval. I could do it as a z-score. So under the null hypothesis, I calculate my standard deviation. So P0 is equal to a half. So I get my standard deviation is 0.05. I calculate my z-score. I get 1.2. That's less than my 1.64. So if I'm doing a one-sided test, so if I go back to my if I go back here, essentially I'm in this zone here, right? I see an observation of 1.2. Anything on this side is H0. Anything on this side is H1. And at the 5% level, my magic level to compare it to is 1.64. So another way of saying it is the data that I've seen, the evidence I've seen, is only 1.2 standard deviations away from what you would have expected under the null, and so it hasn't reached our level of significance. Okay, and again, as a hypothesis test, I will do it as a proportion dot test. Okay, just like we talked about sensitivity and specificity, the same concept is true in A/B testing. There's a type 1 error and a type 2 error. Rejecting a true H0, generally we control the type 1 error. So the 5% in the Neyman-Pearson framework, that's controlled. And again, I keep on mentioning it, but Edwards, Lim, and Savage, when they describe the Bayes approach, points out that controlling this type 1 error really doesn't make too much sense. It should be more a problem of assessing economic costs between these two competing theories. And again, looking at the likelihood ratio between the two. And just a very simple example, I could have two hypotheses, H0 and H1, and my observed data. So I could look at what's the likelihood of my data given H0, what's my likelihood of my data given H1. This could be small, and this could be even smaller. And so if I think about Bayes' rule, P of H0 given D over P of H1 given D is essentially this likelihood ratio, or sometimes called a Bayes factor, weighted by my prior odds of the two hypotheses to be true. So if this is small, but this one's even smaller, you can see that this ratio here will actually be bigger than 1. And so you can see that the evidence in Bayes will actually favor H0 over H1. So a simple example there, so I could have a p-value that's less than 0.05, and yet I would be wanting to, I'd be having a high posterior probability that H0 is true. So this Neyman-Pearson framework of how you set up these type 1 and type 2 errors is crucial, and just the underlying the underlying assumption in it is that I'm controlling type 1 error. Actually, maybe in slight defense of Neyman-Pearson, a lot of it came up in agricultural trials, field experiments in the 1920s. And there you would say, I'm going to do a whole bunch of experiments. And I want to make sure that I've only got a 5% error if I'm planting crops. And I'm going to do it multiple times in multiple plots. I only want a 5% error. So sometimes that objective makes sense. But as a general rule, it doesn't. And the Bayes approach makes more sense. Okay. Here's a nice article from The Economist. You can click on the link. Again, a little bit like our breast cancer example. You can couch all of these things in terms of how many false positives and false negatives do you get. Very quickly, one of my good friends works at CERN in Geneva, so I was lucky enough to go there. And it was at a time when one of these particles was found, the Higgs boson, and what interested me was that the scientific reporting was basically given by a p-value and a z-score. Okay. Just a couple more examples to finish off. We've done examples of small sample sizes. Let me do one with very, very large sample sizes. So it's a famous study of Pfizer, who introduced Viagra in 1998, and 77 people out of a sample size of 6 million. So now I have incredibly large sample sizes, so I'll be able to figure out precisely what the difference in probabilities are, died from heart attack problems. And the upshot from this is that the labeling of Viagra has to have a warning of such things, that it increases your risk of heart attack. How do they figure that out? They took a similar group of people out of 1.5 million, so one quarter, they found that 11 died. Now, of course, 11 times 4 is 44, so the 77 is much bigger than the 44. And again, because I've got very large sample sizes, we're going to see that it's statistically significant. So even though the probability of dying is incredibly small, so your risk of dying is very small, it is elevated. Again, what's the math? What's the formula to plug into? Do a difference of proportions. The risk of dying is incredibly small. 4 zeros and 5 zeros. When I put it all together, the interval does not contain 0. So there is statistical evidence, even at a very low level of alpha, that there's a difference. But of course, the overall level is small. So Pfizer has has to provide warnings on the labeling. Another very common use of A/B testing, I mean, because of the growth of the internet, huge numbers of companies use it. So electronic arts, selling video games, it wants to figure out whether you should use a promotion bias or not. Actually, in some of these studies, sometimes there's what's known as confounding variables. So if you miss another variable, you can get results that sort of look wrong. I think most people buy these new video games at midnight the day when they're announced. So if you get the timing wrong, you can make mistakes. So here was an electronic arts. Again, if you click on the link, you'll see a story. So again, your conclusions are only as good as your data collected, and if you've missed confounding variables and something you've missed, your X bars are going to get it wrong. There's a simple function in R for doing A/B testing. What color background should I have on my website, pink or black? I look at my rates. I look at my sample sizes. I can do the test if I have difference in sample sizes. And the first thing I look at is, how big are my sample sizes? Then I look at the difference, and you can see that there'd be intuitively a difference there. Lots of companies let you run A/B tests on your website. Google Analytics, so big part of Google Analytics. Netflix, again, if you click on these hyperlinks, you get to read all about how a company like Netflix uses A/B testing. So it's all about A/B testing. Everybody's always trying to improve user experience, and deciding what to show in front of you is sort of important. The modern day version of this is something called bandit problems. So when you've got more than one or two options, and you're doing things sequentially in time, there's something called Thompson sampling and bandit problems. So again, a very interesting area. Okay, my last example of A/B testing, sort of one of my favorites. So someone called Lord Rayleigh, who discovered argon. So he won the Nobel Prize for discovering this inert gas. And argon was interesting to me because it really has very few uses. I think it's used in diving, it's used in welding. It's got some, but not much. And he essentially made two data sets. One, he took a sample of air, removed all the oxygen from it, and second, he made a chemical version of it. And he wanted to see what the difference was between the two. And of course, the difference would be this inert gas that's sitting in the atmosphere. A little bit of argon is sitting in his sample. So here's what he got, and he had a very small sample size, so n was equal to 7, n was equal to 8, and so we're going to use a t-distribution. And rather interestingly, the averages looked incredibly close, right? But of course, there's a little bit of a difference, right? So from air will include, this is plus argon in this little box here, right? So the means to the human eye look very similar, even though there's a very small difference and very small sample sizes too. But what's the little trick here? Well, the standard deviations are even smaller. So it's an interesting example, small sample sizes, but even smaller standard deviations, and that's enough to be able to pick up this significant difference between the means. And again, if you just go over the math, you look at compare those two samples, you get a t ratio, well above 1.96. You get a t ratio up in the 20s. The degrees of freedom is essentially n1 plus n2 minus 2. So what, 7 plus 8 minus 2 is 13. And the p-value is very surprising under the null hypothesis that there's no difference, that they would be the same. Let me talk now about a very important topic of observational versus field studies. And the reason this is so important is that lots of data comes to you as an observational study, not as a carefully designed field experiment. And this literature dates back to Fisher and his book Design of Experiments. And it's related to this overall goal of trying to understand causation, or given a couple of variables, which way do the arrows go? Does X cause Y, or does Y cause X, or I guess do the arrows go both ways? So here's an interesting question. Does owning a Tesla mean you have more money in the bank, or does the fact you have more money in the bank mean that you buy a Tesla? Okay, so one approach to try and do this, rather than just an observational study, just from looking at the correlation of money in the bank and people owning Teslas, you wouldn't be able to pass out the true effect. So to do that, I could do a field experiment, randomly pick 100 people, split into two groups, give half the people a Tesla, the other half some other car like a Chevy, and then in 2 years, try and assess that treatment effect, what would happen. And I guess the business school equivalent is Booth versus Kellogg. Okay. 2019 Nobel Prize was given to 3 Harvard economists for implementing these so-called randomized controlled trials that Fisher essentially invented in their experimental economics. And of course, in collecting any data set, it's important to figure out the right question, important to have a carefully designed experiment, and having done that, the statistical, you can simply look at very simple statistical tools for figuring out treatment effects from that. Now, this experimental approach is growing in popularity for obvious reasons. Lots of economic data is just based purely on observational data, not carefully controlled randomized experiments. And they're becoming the gold standard for trying to understand causality. Of course, it's much more costly to collect, to design randomized controlled trials, and generally takes a lot more time as well. So how do we collect field experiments? Randomized clinical trials, they're becoming standard in medicine, in agriculture, and they're becoming now standard in policy analysis. And there's lots of issues about randomization that comes into these trials. So let me look at the Nobel Prize winning data set. So let's look at the Duflo, Banerjee, and Kramer paper. So they were looking at truth telling in India from third-party auditors in response to pollution controls that the Indian government put into effect. And so up here in the control group, a bunch of industrial Indian firms were given a quota, and the quota is essentially sitting here, and they were told to go pay outside auditors to order them, a third-party auditor, to see if they were under the pollution controls. And so there was no government involved, other than the government telling these firms they had to go get a third-party auditor to figure out whether they were under that barrier or not. And of course, you see, maybe not surprisingly, that these third-party auditors were paid by the firms, and everybody was under, except maybe 2 auditors. So maybe the joke here is that there are like 2 honest, truth-telling third-party auditors. So that's the control group. Now, the Indian government realized something was wrong, so the treatment group is when the government itself paid auditing firms to go in and figure out whether people were beneath or below the barrier. And of course, now you get a lot more people that, having audited these firms, realize that they were polluting more than they should. But of course, there's still a group of people here, even paid by the Indian government, that it seems a little bit surprising. So a third randomized approach was given, just to go test both of these procedures and you can see that these two graphs pretty much look the same. And so this is the gold standard of truth, as opposed to what's happening in reality. So the original firms paying auditors themselves was incredibly corrupt, and rather amusingly, there was still some corruption left over when the government was paying these firms. And simple statistics is just essentially looking at histograms. There's nothing more to do there. So rather interesting. Just one more example of that. A field experiment was done for looking at electoral fraud in Russian parliamentary elections. So there was a treatment group and a control group. So independent observers telling the truth were assigned to 156 of the 3,164 polling stations. Putin's United Party is sitting here. You can see that in the treatment group, so truth is down here, and 95% confidence intervals have been placed. So you can see that Putin's party was getting apparently 45% of the vote. Apparently that was the magic number that was pre-assigned, whereas in the independent order it was more in the 35% range. And it's rather interesting to see, where did that excess come from? Well, one part of the excess came from the turnout, and so that was people suspecting that more ballots were stuffed into boxes. And the other rather interesting fact that it seems as if some of the votes were taken away from the Communist Party. So again, just looking at difference in means from a treatment group and a control group, and just looking at confidence intervals. Okay, let me finish this week with a little precursor of what's going to happen for the next few weeks in the course. And so let me talk a little bit about machine learning, and let me talk a little bit about pattern matching from empirical data. So again, the last 10 years has seen an incredible explosion in such things. And one of the interesting problems is you'll collect some empirical data set of input-output pairs, and you'll have a whole bunch of possible predictive variables, P variables, and P can be very high dimensional. And that's partly because P might contain all interaction terms, or what's known as dummy variables, indicator variables, etc. So you can create a lot of variables. And the whole idea is, how do my input variables predict my output variable? And you want to do what's known as find features, or what used to be called principal components. And so features are essentially just linear combinations of predictors that have significance in predicting Y. And the multiple layer version of that is something called deep learning, which we'll get to in the last week of class. So again, a lot of observational data sets exist. I have n inputs and n outputs, and I want to find some functional relationship of how does Y relate to X. And there'll typically be some set of parameters that I will tune or train on a training data set. And so one problem that you'll see us talk a lot about is in the training phase of a model, how do I find my parameters? If it was a linear output, it would be my regression coefficients. I do it by minimizing some L2 norm, and that's something called the principle of least squares that Gauss figured out. And coming up next is linear regression. So the simplest possible case is Y is equal to an intercept plus a slope times a variable, and there's Gauss's classic least squares, and there's a solution for this. So B or beta 1. And then one other important concept to realize that took over in machine learning is more of a predictive culture in these problems. So rather than worrying about causation, trying to figure out, does X cause Y or Y cause X, looking at models and saying, okay, a model is only as good as its prediction. So a good prediction in lots of business problems, machine learning, algorithmic problems, I'll look at out-of-sample predictive mean squared error. So what's a what's a good criterion. I'll have a holdout sample, and having trained my model using least squares or fitting a deep learning model, say, I then look at predictive mean squared error. And this can lead to very complex functions, F, and there's a race to find good predictors, deep learning, tree models, something called random forests, which is a generalization of tree models. And as I say here, it seems as if economics is moving more towards this predictive culture as well. And so there's a summary of today: estimation, confidence, prediction intervals, A/B testing, and the next lecture we'll talk about least squares and regression. Thank you very much. Thank you for listening.